actually founded in 1961. Now, what the gemstone estimator does is it pulls the estimator closer to the targeted value, and in this case, would push it towards the value we're estimating, or the actual value. Therefore, in a quest to actually study the gemstone estimator for the exponential regression, first would actually look at the maximum likelihood estimator for the exponential regression. Now, we need to understand that.
Just 1 minute.
Yeah.
I don't know. You used this LaTeX?
Yep.
Okay. But this now.
Yes, it's LaTeX.
This bracket. You see this curly bracket? I want from here, from this positive here.
Okay.
Let me enlarge it, right?
Yep. Okay.
So you can see it fully.
Mm-hmm.
And so I want from this, after this plus,
Mm-hmm.
to just come to the next, to enter it to the next.
Let's continue with your presentation.
Okay.
I'll continue. Yeah, please.
Let's try that.
You tried slash.
It's because
Okay.
because of this full bracket. If from here, I can do that when you
so
but from because of the
Adam,
this
can you
bracket,
move?
slash doesn't work there. But I know
Adam, can you mute yourself, please?
You
Adam.
have to do slash new line.
Okay.
Otherwise, I would.
Let me just.
Okay. So we'll start with
as the administrator.
You see the slash here.
The host.
Try slash new
okay.
line.
So I'll start with the exponential model and how we get the maximum likelihood estimator for the exponential regression. We know that the exponential regression is a non-linear regression, and therefore to get a maximum likelihood estimator, it's not an easy task, because we would require to use methods like Newton's method, EM algorithms, and other methods for iterations. Therefore, in this presentation, I've actually used a method which is used in bridge regression. And if we use what we call the alternative reweighted least squares estimation, would obtain a maximum likelihood estimator for the exponential regression, which is actually given by the equation number 5. And that equation, where X is the design matrix, Y is the response vector, and W, which is presented as an estimate, is a diagonal weight matrix. The matrix W is updated iteratively using the equation in 6, because we know that to actually get our maximum likelihood estimator, we need to iterate until we have a convergence. That's when we'll be able to get our maximum likelihood estimator. Because this is what will give us a chance of shrinking this estimator in order to come up with another estimator, which is a shrinkage estimator, which we call the exponential gemstone estimator. Therefore, if we look at equation 6, we would be able to also see that we are, for the estimate for the weighted matrix W, we are just getting the elements of the diagonal of that matrix, which can be actually estimated furthermore when we let mu equal to yi and over x bar. That is when we consider each response of the regression. So to explain more on that, the elements of the response matrix Y would be given by equation 7. And that is direct from the exponential model, where Yi is the ith element of the response matrix Y, and the small yi is the ith observation of the response variable. Then the small xi is the ith row of the design matrix X. And the estimate of beta, because beta will be our coefficients for the regression, and therefore the estimate of that to the power k minus 1 would actually represent the estimate of the regression coefficients at the k minus 1 iteration. And that would give us the process of iteration for that convergence. Then k would actually represent the current iteration. Now, if we have that iteration, it would be important to look at how equation 7 would reduce if we substitute mu, which we rated as yi over xi b to the power k minus 1. And it would reduce to equation 8. And also, we'll let T, capital T, equal to that matrix, which is given in 5, which is the design matrix, the transpose of the design matrix times the weighted matrix. And getting it from there, we would see that we can easily take advantage of T, looking at its structure, that we can have a spectral decomposition, which will be in terms of two matrices, Q and capital lambda, where Q would represent the matrix whose columns are the eigenvectors of T, while capital lambda will denote a diagonal matrix containing the eigenvalues of T. So we would have eigenvectors because we are in a multivariate case, and then the other one would represent the actual eigenvalues, which are represented by lambda 1 up to P. And since P would be our dimension. So since we are looking at forming the James-Stern estimator for the exponential regression, and see to it on how it would be actually of help on trying to reduce multicollinearity, which comes as a problem when we are considering a maximum likelihood estimator. It is important to look at the properties of the maximum likelihood estimator for this exponential regression. So if we consider that, we would see that the mean square error of the maximum likelihood estimator would be computed as shown in equation 9. It would be simply the representation of the inverse of the matrix T, which we looked at in equation 5, 6, and 7. And then the expectation of the loss would be given by the expectation of the maximum likelihood estimator minus when we find the difference with the parameter we are estimating. And since these are matrices, we would get the transpose to get that. And when we compute it and simplify it, it will actually give us that the expected loss for this maximum likelihood estimator for the exponential regression would reduce into the summation of the inverses of the eigenvalues. Of course, a lambda j would represent the jth eigenvalue of t. When there exists a high correlation among the explanatory variables x and the weighted matrix of cross products of t, we would know that the maximum likelihood estimator would not actually do a good job in estimating beta. Therefore, with that, we can look at the exponential Gemstern estimator, which I'm calling AGAS. So using the James and Stern technique of 1961, we would know that to shrink the maximum likelihood estimator B hat would actually require us to choose a coefficient would multiply it, which would be between 0 and 1, and then gives us the advantage in the mean square error. So if we do that, the best choice or the optimum choice, according to James and Stern, would be K, which is equal to what is represented in equation 13. With the choice of K, would try and look at the maximum likelihood estimator and the exponential James-Stern estimator and see what we would have if it would be biased or not. And if we get the bias mathematically or statistically, the bias is actually calculated by getting the expectation of the estimator, and we subtract the parameter it is estimating, which is the representation in equation 14. So our expected value of the exponential James-Stern would be actually the expected value with that coefficient K, which is shrinking the maximum likelihood estimator, and we subtract the parameter or the coefficients of regression it is estimating. Therefore, with that bias given, then we can easily look at the properties of the exponential James-Stern estimator in terms of the mean square error. So the mean squared error is calculated by the variance of the estimator plus the bias of the estimator. Now, if we look at equation 14, we can easily simplify it using equation 9, 10, and 11 to have what is shown in equation 15, which simplifies to the negative of the trace of the inverse of t, meaning we are getting the sum of the diagonal elements of t, and then we are also getting the product of what we are estimating, and since it's a matrix, the transpose times the other matrix of beta. And this matrix, we know that it would be a p by 1, and the other one, if we get the transpose, it becomes a 1 by p, and therefore ending with a 1 by p matrix. And then we add the trace. And when this coefficient would actually be shaping up what we are estimating. So that is what we get when we simplify equation 14. Then with the bias in place, we would have the mean squared error of the exponential James-Stein estimator given by the variance of the exponential James-Stein estimator. Sorry, there where this P is supposed to be S plus the bias of the exponential James-Stein estimator, which is represented by the equation 16. And when we simplified using equation 11 and 15, since in those equations we explicitly presented the bias, it would give us the mean squared error, which would be a summation of the alpha and the lambda. Now the alpha would be the coefficients if we have an exponential. So that sum in equation 17, if we look at it closely, it actually gives us a scalar, not a matrix. And that scalar would represent our mean squared error for the exponential James-Stein. So if we have that quantity, then we can theoretically compare the mean square error of the maximum likelihood estimator and the mean squared error of the exponential James-Stein. So theorem 1 gives that if we have a multivariate exponential regression and the bias as discussed earlier, the difference of the mean square error of the maximum likelihood estimator and the mean squared error. Yes?
Alex, you have 3 minutes left, okay? 3 minutes left.
Okay, noted, Prof. Thank you very much. So it would actually be greater than 0, meaning if it's greater than 0, then it means that the exponential James-Stein estimator has got a minimal mean square compared to the maximum likelihood estimator. If we go through the proof using equation 11 and 7, the difference, we subtract the difference, and it would give us an equation in equation 19, which we can simplify further using the scalars of the mean squared error. And if we simplify them further, we can analyze that the first term in equation 21, and since we had also the bias, this difference would turn up to be a sum, and since the first term would be positive, it will give us a quantity greater than 0. And since it gives us a quantity greater than 0, it means that the exponential James-Stein estimator dominates the maximum likelihood estimator in an exponential regression. So comparing the properties, the expectancy is that both the exponential James-Stein and the maximum likelihood estimator are consistent. Also, both the exponential James-Stein estimator and the maximum likelihood estimator are asymptotically efficient. This would be gotten from the properties of the maximum likelihood estimator, as shrinkage would not change these properties. And then in terms of the mean squared error, we have already seen that the exponential James-Stein estimator will have minimal mean squared error. Conclusion: since the exponential James-Stein estimator has minimal mean squared error compared to the maximum likelihood estimator in a high dimension exponential model when estimating the regression coefficients beta, this will mean that since multicollinearity brings affects the mean squared error, then it will mean that shrinking the maximum likelihood estimator would actually take care of a problem of multicollinearity. That's where the presentation ends. Thank you.
Thank you, Alex. Any questions for Alex, please? Hello, guys. Any questions for Alex?
Hi.
Hello.
Yes, thanks for the presentation. Really nice. Since when you look at the mean square error, there's a variance and the bias component.
Yes, yes.
Yeah. So, and we've always assumed that the maximum likelihood estimators are the best estimators, consistent estimators, and the like. How do you compare the
Yes.
bias?
So in terms of the bias, the shrinkage estimator, which is the exponential Gemstone estimator, would be biased, and it is this biasness which actually gives it an advantage of having minimum mean squared error. So
Yes.
would trade biasness with effectiveness, and say that in terms of effectiveness, the shrinkage estimator would be actually closer to the true value, since it will have minimum mean squared error.
Yes, I hear you. But what properties
Thank
are
you
you
very much.
what properties are you interested in when you're looking at estimation? Because you remember when you're looking at estimation, you're saying if you consistently select a sample, you
Okay.
want that estimator to be unbiased.
Okay.
Yeah.
Okay. So in this case, our attention goes much to the problem of exponential regression in high dimension, which brings about multicollinearity. So in this case, the exponential Gemstone would be better because it will deal with that problem of multicollinearity. So I take it that it depends on the problem you are dealing with. So in other problems, the Gemstone shrinkage estimator would do better because it would look at the most effective way of dealing with the problem with that model.
Okay.
Thank you very much.
Any other questions for Alex? Yeah, one question I have, Alex, is did you do like simulations to confirm the performance of the proposed estimator with other estimators?
I think that's a good. Actually, I wanted to ask that one because you just done the theoretical framework, but then you haven't looked at a case scenario with data or through simulations. Thanks for asking that.
Okay, thank you very much. I did simulations, though I didn't finish because I wanted to compare not only with the maximum likelihood estimator. I guess this exponential regression, would have other biased estimators apart from the Gemstone estimator. So my data for the two I did, and it was doing well, but my data unfortunately got crashed out and I couldn't retrieve those. But with time, I think I can retrieve those and redo the simulations. So I started with simulations before I came up with a presentation.
Okay, thank you, Alex. So let's move to the next talk because because of time.
Thank you very much, Prof.
Yes.
Do you have a case study or data which you can use to, apart from simulations? Because one has to see the relevance of this. That's my, yeah. And then I'm looking at the methodology that you've gone through. It's something that was developed. What has been your contribution to this particular aspect? Because I've looked at the Gemstein estimator in terms of how you actually estimate it. It's exactly how you've done it. So I want to look at what is your specific contribution to this.
Okay. So, for the real case, a real case of data, since exponential regression estimates the Poisson in terms of the count, most of this has just been done on the Poisson process or Poisson regression, where a lot of bridge estimators have been done. So my strength on this would be actually be specific on the exponential regression itself, because as a model, it is very important when we look at, especially in health cases, when we look at maybe recovery periods, it would be very important, instead of using a Poisson, we use an exponential in other scenarios.
Yeah, no, thanks a lot. A very nice presentation. Yeah.
Okay, thank you very much, Tobias.
Thank you, guys. So let's move on to the next presentation. It's by a brother from Ghana, Jack Prick. Can you start your presentation, please? Jack Prick, are you there?
Yeah, I'm here.
Okay, thank you, brother. So he's going to talk about estimation of finite population mean using non-median of an auxiliary variable. Thank you. Thank you, Jack Prick.
Good afternoon to you all, and thank you, Prof, for the opportunity.
Yeah.
Can you see my screen?
Yes.
Yeah,
Yes.
yeah, we can see.
Thank you. Yes, I'm Jacob Dioban from the University of Technology and Applied Sciences in Navrongo, Ghana, here to make a presentation on the topic, estimation of finite population mean using known median of the auxiliary variable. I'll take you through introduction, methodology, and then draw some conclusions based on the applications of the result that will be generated through the study. Then, generally, major decisions in the world over are made based on the values of means. And that is why mostly in health, you'll be talking about life expectancy of men and women in given countries, which are mainly average number of years, both gender or sex, they can't live within that time. Average number of people who fall below the poverty line in a given country, taken as a measure of standard of living, and the average number of maternal mortality or neonatal deaths, as well as infant mortality, are all indicators that are based on the mean of populations for a coherent administrative and planning decisions. So therefore, this has always been a major concern to survey practitioners in improving the precision of mean estimates. And that led to proposals of many estimators for improving same. Far back as 1940, Cochrane proposed the ratio estimator, which is just the ratio of the population mean to that of the sample mean multiplied by the auxiliary variable multiplied by the steady mean of the steady variable. A number of modifications did happen with a view to improving the efficiency of the ratio estimator once it is already known to be generally biased. But one that is of interest to me that I've quoted as part of this study is the one that was proposed by Ball and Tituja in 1991, where he took the difference of the population and the sample means or the usually variable and divided by its sum, then multiplied by the steady variable. That indeed resulted in a great improvement in the precision of the mean estimate, but also had some bias. Now, generally, most of those common estimators in practice or in existence are actually being derived based on the sample and population means of the steady populations. But we know that the sample mean or the mean in itself is susceptible to outliers and other characteristics of the population. And therefore, any estimator that is based on the mean itself is still also liable to yielding or wielding significant bias, and therefore will also not be that precise. Consequently, Subramani in 2016 proposed a median ratio estimator, where he simply replaced the mean and the means in the common ratio or conventional ratio estimator by the medians. And that resulted in a significant improvement of the bias and precision of the estimator. Now, motivated by this, I propose a modified ratio estimator, which is the mainstay of this study. And the intention is to ensure that we improve in the bias as well as the precision of the mean estimates. So at least some few of the methods that will be used in this study. The fundamental building block will be the ratio estimator, which is given in equation 1. And then we'll also be using the binomial expansion given in equation 2. Then we use the relative percentage relative error to assess the level of performance. Now, given that the capital M is the median of the population, and then small m is the median of the sample, equation 4 is the form of the proposed estimator, following from the proposed estimator by the estimator of Subramani of 2016. Fortunately, I think Alex and Victor had already defined he stated the large sample theory in his presentation. And then based on those properties, the following relations or the relative errors also holds. That is illustrated in equation 5. Now, if we make the substitution of the definition stated in the relation stated in equation 5 into the proposed estimator, we obtain equation 6, which is actually the form of the proposed estimator. But we know that generally bias is defined as given in equation 7. I'm not repeating the explanation because Alex indeed emphasized on the composition or the procedure to obtain bias. So it's given in equation 7. Making relevant substitution and simplifying yield the bias of the proposed estimator as in equation 8. Then the mean square error is defined as the expectation of the proposed estimator minus the mean or squared. Then making relevant substitution and simplifying, we obtain equation 9 as the mean square error of the proposed estimator. But then this alpha is a scalar, which seeks to improve on the convergence of the proposed estimator. Therefore, there's the need for us to obtain the optimal form or value of the alpha that will ensure optimum performance of the proposed estimator. So to obtain that, we take the derivative of the mean square error of the proposed estimator with respect to alpha. And this is given in equation 10. If we set the derivative or equation 10 to 0 and simplify, we obtain the optimum value of alpha as in equation 11. Now, empirical checks reveal that the optimum value of alpha ranges between 1 and 2 or hover around 1 and 2. So therefore, it was important to obtain the bias and mean square errors for these specific values of alpha for 1 and 2. And for alpha equal 1, we obtain the bias as given in equation 12, followed by its mean square error immediately. Then for alpha equal 2, using the same analogy, we obtain the bias of the estimator as given in equation 13, while that of the mean square error is given in equation 14. Of interest in this is that if you look at the bias the gamma is actually 1 over the sample size. So for it repeating in each of the terms means that the limiting value of the bias is actually 0 if n approaches infinity. And the same can be said of the mean square error. It means that it is actually consistent and also possesses the minimum bias property. That we need to be sure its relative performance, compare its relative performance with the estimators that are already in existence. And therefore, compare the proposed estimator with that of the ratio estimator of Cochrane 1940. And for the proposed estimator to be more efficient than the conventional ratio estimator, it means it must have minimum mean square error. So making the relevant comparison and substitution and simplifying, it reveals that the proposed estimator will be more efficient than the ratio estimator if equation 15 holds tight. That is, the correlation between them is less than the terms on the right-hand side. By the same analogy, the proposed estimator will be more efficient than that of Ball and Tütiger of 1991 if equation 16 holds true. And finally, but not the least, the proposed estimator will be more efficient than that of Subramani 2016 if equation 17 holds true. So even though the theoretical construct proposed or suggests that the proposed estimator may be more efficient or will be more efficient than the existing estimators, there is a need for us to do some real-life applications to assess its performance. So to that effect, three populations were used. 1 and 2 were based on wheat production. Wheat production was actually the amount of quantity of wheat produced was a steady variable, and the land cultivated is the auxiliary variable for two populations in 1970 and 1973. No, 1971 and 1974. And then the third population is actually about student performance in exams. And these three populations were used to assess the performance of the 5 estimators. So in the first one, the bias of the ratio estimator is seen to be very high in all three populations, and that is to be expected because the ratio estimator is already known to be biased. But followed by it was the Ball and Tütiger, which indeed, although better than the ratio estimator, but also with significantly larger biases. But the proposed estimator at alpha equal 1 actually produced the least bias among the three estimators, and they were comparatively very consistent to each other, followed by the proposed estimator at alpha equal 2. Even though the alpha equal 2 had a minimum bias next to only next to the alpha equal 1, but of interest was that whilst it has a bias of 14.78 in population 1, it has a bias of negative 3.58 in population 2, and even went further to negative 9.0 in population 3. Although it is not the only estimator to have produced a negative bias in population 3, but the trend of its occurrence is what actually raises concerns. So we therefore go to assess the mean square errors of the estimators based on the same three populations. And again, the ratio estimator had the highest MSE, followed by the estimator of Ball and Tütiger, with the minimum or the least MSE now obtained in proposed estimator with alpha equal 2. So the next estimator with the minimum MSE was the proposed estimator at alpha equal 1, now followed by the Subramani of 2016. So although the proposed estimator at alpha equal 2 was not the best in terms of minimum bias, it turned out to be the one that is the most precise, if I have to say. Then we'll now assess the relative percentage relative errors of the three estimators. And it shows that all the estimators are superior to the ratio estimator, but the proposed estimator at alpha equal 2 indeed emerged as the most, the estimator with the high precision, followed by the proposed estimator at alpha equal 1, and then Subramani in that order. So in conclusion, the proposed estimator produced low bias and MSE. And then the proposed estimator had the lowest bias at alpha equal 1, whilst alpha equal 2 had a minimum bias, which implies that it may be good for estimation at alpha equal 1, and indeed may be good for inference at alpha equal 2. Thank you all for giving me audience.
Thank you. Thank you, sir. Thank you, sir. So, any questions for Jack Pirek? Very interesting talk. Mm. Hi, guys. Go ahead with your questions, sir.
Very interesting talk. Just curious about the proposed 1 and 2, and on population 2 and 3, the way they went to the negative values. What would you attribute that to? Because it was really interesting in those ones.
Yes. You see, like, thank you for the question. The proposed estimator at alpha equal 1 is actually a dual estimator of the ratio multiplied by its what is the square root? Positive say what is the square root estimator? Then that's of the square that of the alpha equal 2 is actually the square of the proposed estimator. So it means that the mean square error estimator may have higher orders in alpha equal 2 than it is in alpha equal 1. So, but the reason why I'm not able to make a coherent or conclusive statement on what might have caused that is because it is a real data and not a simulated data. I could not establish exactly the behavior of the rule, because what will influence the performance of the estimator will be based on the correlation coefficient, which could not be which I did not assess in the two populations. But a simulation study is underway. By the time I complete that, I'll be able to tell coherently what indeed may be causing those occurrences. Thank you.
Thank you. Yeah.
Any other questions for Jack Pirek?
I was wondering, just out of curiosity as well, on the choice of alpha is equal to 1 and alpha is equal to 2, and wondering what would happen if this alpha here is chosen somewhere between 1 and 2. I don't know whether you considered looking at a situation like that and what would happen.
Yes, thank you, Victor. That's an interesting question. Yes, actually, because it was hovering between those two numbers, means that there's actually an exact value that will optimize the performance of the estimator. And that is the mainstay of the simulation study. So that whatsoever the figure is, I'll be able to do that, in which case we'll have to now incorporate the optimum, so to speak, in quote, optimum estimator to compare together with the 1 and 2. But for theoretical convenience, I limited that to the whole numbers. Thank you.
All right. Yeah. If there are no more questions, the next speaker will be our lovely, our own Kingsley is going to be the next speaker. Kingsley, you ready?
Yeah. So I did this work with quite a number of other African scholars. So I'm allowing one of those who were participating in the program to present. This was sponsored by the mathematical IMU, Committee for Women in Mathematics, International Mathematical Union, International Mathematics Union. So we had this 1-year mentorship from January till now to look at issues relating to work-life balance of women. Women in mathematics. We know that women in mathematics have a lot of. Fumi, are you around? Hello, Fumi.
Marand.
Please,
Good
please
day,
start.
everyone. I'm Marand.
Okay, please start sharing your
I'm
screen.
here.
Okay. Share your screen. Share your screen. We did this work because we know a lot of women in mathematics are not showcasing themselves in terms of research, and after looking at the issues, it's been well documented in literature that the work-life balance for women is highly skewed because of especially African women. And so there's so much little research that they have so little time to do any quality research. So not much has been looked at in terms of for African women. So that is what we actually delved into, and this is the findings we came up with. So I will allow for me to take over and present. Thank you. Fumi, you can go on now. Your screen. You are.
Good day. All right, Ma. Thanks so much for the privilege. Good day, everyone. My name is Adewale Funlayo Omolara from Nigeria. I'm here to present a research work titled Institutional and Societal Factors Impacting Work-Life Balance for African Women in Mathematical Careers. Yeah, these are the co-authors from 5 different countries. We have Dr. Quinsley Shukundum from Nigeria as the research group leader and facilitator. Yeah, this is a diagram showing a woman in mathematics with work and life in a beam balance. The outline. We have, I will take you through introduction, literature review, data analysis, and the recommendation. Introduction. Work-life balance. What do we understand by work-life balance? It's a term used to describe how workers distribute their time between professional and personal obligations. As it was observed in African countries that participation of women in mathematical career remain low due to some factors such as lack of education on mathematics, barriers in mathematics such as discrimination gender-based, lack of representation in leadership position, and lack of general support from institutional system, which discourages female students from pursuing STEM career. Problem statement. For women in mathematics, juggling the demand of family and careers, goals might be difficult. Making a work-life balance remains a critical issue for professional women around the world. Our assessment on the research is to examine the experience of female mathematicians who have combined professional with personal obligations, or those who are just pursuing it. Objectives. The objectives of this research are to conduct comparative analysis work-life balance policies across 4 institutions, which are the government, the non-government institution, the private institution, and academia. Also to examine institutional practice through policy demands and reports. Reviewing institutional practice from the survey based on the 4 categories of institution mentioned. And lastly, to develop a detailed and tailored institutional policy recommendation for systemic changes of the 4 categories of institutions. Then we have our literature review. We have several literature reviews here, but I will take one, which is Gozek 2019. The GOZE 2019 used a modified method that combined life history with interview of participants as well as their experiences with starting a family, parenting children, and the time frame. That's what GOZE 2019 discussed on the title Life and Career. Yes, I will move to our research gap. Our research gap is from the literature reviewed above. The need to study work-life balance of women career in mathematics and similar fields under larger cultural and institutional issue cannot be overemphasized. Therefore, there is need to examine the larger institutional and sociological elements influencing women's career in mathematics. Data analysis. Here we have the visual representation of policy implemented by the 4 institutions, which are academia, government, non-government, and private sector. We have the visual representation of the policy implemented by the 4 institutions. Yes, on institutional policy. Here, the visual representation of the policy implemented by the 4 institutions, which are government, academia, non-government, and private. Yes, this analysis was done by developing a Google form as a questionnaire to women across different countries, 5 countries, African countries, and UK. So the question was designed for women in mathematics and related fields, but mathematics in particular. Among all those questions that were given, we have flexible working hours, which is the most implemented policy. We can see from the diagram. I'm trying to enlarge it so that we can see through. These are the respondents. Then we have flexible working hour, which is prioritized by the respondents on government institutions. Yes, we have about 46% of them. If we check through academia, we have 47, which is taking the larger part. And on non-government, we have 38, and on private, we have 29, which is taking more of the larger parts from the respondents. So from these, we can see that the most implemented policy is a flexible working hour, making it clear that many value flexibility in their work. And when compared, the next is the wellness program, which the respondent, the women, also prioritize in their working place. But compared to the institutional childcare services, which has a very low respondent, or yes, for women in mathematics, where they are not being provided where they will keep their child, and it's actually affecting their work. So with that, also, we move to the next one, which is also the comparative analysis on work-life balance policy based on the 4 categories also. That is the institutional support system. Also, we can see from here, the flexible working hour too. It's more flexible hours is actually prioritized across the 4 institutions. And the next one is the better health care. Also, if we look at those things, we can also see that the child care and personal matter of the women are not prioritized in any of the organizations. So we can see that flexible working hour is highly favored, unlike the personal matter and child care services, which are not prioritized at all, compared with the flexible working hour and telecommunity. If you look through the charts. So this has brought us to a logical relationship with between different work-life balance strategy and policy. What brought about this was that in some questions, the respondents was provided the opportunity to choose more than one options, which is highlighting the complexity of their experiences and perspective to effectively capture the relationship among this selection. Then a Venn diagram was employed. The visual representation gives a clearer understanding of how individuals intersect their responses across multiple options. From this Venn diagram, from this representation, we can see that flexible working hour is highly favored with wellness program, then telecommuting. So we can see from here, the data indicate that flexible working hours are favored as the primary strategy for work-life balance, followed by its combination with wellness program, which is highlighting an opportunity to promote wellness program initiative more effectively among workers to enhance their appeal. Also, women are facing some challenges also in their, I've explained this. Yeah, they are facing challenges in work-life balance strategy and policies too. These are the challenges. The challenges here is represented as family exploitation, work culture, lack of institutional support, and society norms. Yeah, these are the challenges women are facing in mathematics. In the fourth Venn diagram, family expectation and work culture remain dominant challenges women are facing, which accounting for 19.15% of responses. And when combined with the family expectation and work-life balance, it increases to about 21.28%, which indicates a strong overlap in challenges of many individuals. Then the second Venn diagram also, we have family expectation, work culture, and lack of institutional support. Yes, the lack of institutional support has a lower responded, but when combined with work-life balance and work culture, it skyrockets to about 21.28%. So it is now coming to conclusion that the challenges women in mathematics face in maintaining work-life balance are family expectation versus work culture and societal norms. I've explained this. Yeah. So this has brought us to a recommended tailored institutional policy with this our research. And the tailored institutional policy recommendations on the 4 institutions. We have academia, government, then non-governmental organization, and private sector. So if we say through this tailored institutional policy recommendation, we can see flexible working hours is highly prioritized by the respondents. And then combined with also the next is the mentorship program. More women should be encouraged to have a mentorship program where they can actually increase in knowledge, even to have to be familiar and to have better understanding of their work and how to balance it with their family. So in this institutional policy recommendation, we can see institutional child care services as a low recommendation from all the 4 institutions. So to our conclusion here, we can see that more flexible working hours with working in shifts should be given to women to achieve work-life balance. Also to create a wellness program which enables women to share issues that they face personally and professionally. And lastly, institutions should try and build a child care facility at work for women, for nursing women in mathematics, which can make them to put their energy in their work and at the same time to be able to check on their child during break to see their children or child. These are the references that helped in the research, because we don't have an in-depth non-existent of data in this research. So, but this is what has helped us so far. And lastly, I have a quote which says, "No one on his deathbed ever said, 'I wish I had spent more time at the office.'" So from my side, I wish everyone should just put their work and balance on a beam and have a good day. Thank you for listening.
Thank you very much. Really inspiring talk. Very, very inspiring talk. Any questions? Any questions for the speakers?
Okay. So can I come in?
Sure.
Okay, thank you. Thank you. Let me know if I get your name wrong. Fumi.
Fumi Layo.
Fumi. Okay, thank you. Thank you for a nice presentation and a nice work. Congratulations to your team.
Thank you.
Anything that has to do with women welfare has always been central to me. And I keep telling my colleagues that if you are at the workplace and you are the same rank with a woman, know that the woman is your senior, because they even work and sleep. How did you come by the variables that you use as the focal points in the Venn diagram? You know, you have something like family expectations and all that. What I was expecting was that you could use a certain data reduction technique, maybe could be factor analysis, then you prune them down to the major ones. And once you know they are the major ones, then you'll be able to now elaborate more on their effect on the women career expectations and all that, instead of just lumping them from the top and then trying to do that comparison. The frequencies are good, but they don't tell the whole story, as if you were using those kind of conventional analytical tools. Thank you.
Thank you, sir.
Okay, maybe I should come in here. Actually, because this work is meant for policy makers, so we tried not to bring in quite some level of mathematical or statistical. I mean, we drastically reduced the amount of statistical or mathematical methodologies that we infused into the work. But with this set of questions, I mean, with this set of options variables, there were a few variables that were asked. There were not much variables. So based on that, from the responses, from the survey results, you know, like the exploratory analysis, you would see from the bar chart, you would see how the responses were. So since there are very few, there are not much variables in terms of trying to find the different distance. So we just decided to use that with an eyeball, eyeball check. One can see which ones are more, which ones are distant. But the bar chart did not help us to understand the interaction between the different options. So this one of the simplest easiest way that I could think of, and we sat on it and indicated. We looked at other policy documents, what they use. Sometimes they use this point XY axis, and then they also use Venn diagram. So Venn diagram was something that looked like an easy way for somebody to understand. But I think going for where we may want to do a much more detailed analysis mathematically, that would work. Thanks for bringing that up. That will be something we'll keep in mind to use. And I forgot to mention that crafts in Malawi, and there's crafts in Malawi also was a sponsor of this project as well. There were 10 different things, 10 different research works that came out of it. This was my group was two of it. So this is one of the ones that came out from my own personal group. And this covered like 7 countries. So we surveyed respondents from 7 different countries, and we had about 69 respondents. Gathered about 69 respondents from the different institutional categories. Yeah.
Thank you, Kingsley. Any other questions for the speaker and Kingsley?
Hi, thanks. This is Tobias. I think like the previous speaker said, I think this is quite nice to see work done by women scientists in our profession. And also for me, it's nice to see Queensley letting somebody lead on the presentation and the work. I think it's really important. But my comment will just be to say, I think sometimes we can underestimate the understanding of our policymakers. I think what we've done is really excellent in terms of describing the data. But in terms of models, they would also understand those. So I think it's important to just go a little deeper in terms of models, looking at factors that can associate these particular outcomes. And I think that from what you said also, it shows to me that as statisticians, we have a critical role to build capacity for not only statisticians, but non-statisticians, so that the understanding is also upscaled. But really, thanks for this. It was really lightening to see the work. Thank you.
Thank you. All right. Yeah, thank you. All right. The next presentation is gonna be by Tolu. Tolu, are you there?
Yes, I'm here.
Hi. Tolu is from the University of Illinois, Urbana-Champaign. She's a mathematician. She works in actuarial science, insurance, and everything. It's really honored to have Tolu here talking. She also gave a talk last year at this workshop. Over to you.
Thank you very much. Good morning, good afternoon, everyone. Can you see my screen?
Yes, we can.
Okay, thank you. Thank you for organizing the second edition. It's always a pleasure to be part of this community. So today I will talk on this project, which is a framework for measures of risk under uncertainty. And this is a joint work with 2 of my colleagues, Sorudo Wang at the University of Waterloo in Canada and Yang Liu at the University of Hong Kong. So the motivation for this particular project comes from the fact that when a risk analyst wants to assess the potential loss in a portfolio, it's natural for the analyst to consider different sources of information. So in most cases, this assessment is not only based on the specification of risk, but then on different information. But when we look at risk measure is mainly defined on a set of random losses, basically mapping risk or a number, mapping like a risk via model to a number. So in this project, what we develop a framework whereby the assessment of risk is jointly based on not only on the set of random losses alone, but also we consider a set of plausible probabilities or set of plausible scenario. And we call this particular risk measure generalized risk measure. So in my talk today, basically what I'm going to do is I'm going to introduce generalized risk measure, and then I will try to characterize this risk measure. And then we go back into the literature and then look at well-known risk measure. For example, the coherent risk measure and try to define and characterize coherent risk measure in this particular framework. And then I'm going to talk about law invariance. So law invariance is another way, it's a part of, is one of the properties of risk measure. And what law invariance basically tells us is that if I have two portfolios, I have X and Y, and X and Y, they have the same distribution, I'm going to assign the same risk value to these two portfolios. But now when we are considering uncertainty, like in our framework, the question is, what would be the right formation for law invariance? So I'm going to introduce to you the different type of law invariance that we have in this particular framework. So let's start from what we know in the literature. So X here is going to be my set of random losses. And so X is a set of random losses in an atomless probability space. And then a risk measure basically map a risk via a model to a number. And risk measure is used for regulatory capital calculation, insurance pricing. So basically, if you want to assess or calculate the potential loss in a portfolio, that is risk measure. And then again, is used again to determine, let's say, the assets or the currency that the financial institution want to keep in their reserve for regulatory purposes. So, and then classical risk measures. So classical risk measures are defined, again, like I said, on this set of random losses. So if you go back, let's come back here. So this is my risk measure, classical definition, only defined on this set of random losses.
Your slides are not moving.
Oh, what about now?
It's still the same from my end.
Oh,
Okay.
okay.
Same. I think the first page. Oh, no.
Yeah,
Oh,
still
the
on the
first
first.
page.
Yeah.
Okay. Then let me stop sharing and start all over again.
Okay.
Okay, so let me start again. And how is it now?
Okay,
Yeah,
now
no.
it's
Fine.
now it's
Yeah,
fine. Yeah,
Okay,
now it's
now
fine.
it's moving. Okay, so I'm not sure whether, did you see this second page, this go?
No. Okay.
No,
Yes. Yeah.
sorry.
You can start from the second page onwards.
Okay. So basically, it is more like the goal. And what we did in this particular paper is that we define risk measure, but now instead of just defining risk measure on a set of random losses that we all know, we define risk measure jointly on a set of random losses and also on the set of probability measures. So basically, we are trying to factor in model uncertainty in our definition for risk measure. And then we call this particular risk measure generalized risk measure. And another thing I'm going to introduce to you today is that, so I'm going to go back to the literature and then we look at classical, maybe coherent risk measure, and then we characterize coherent risk measure in this new framework that I'm going to introduce to you in 2 or 3 minutes. And then I talk about law invariance. So law invariance is another property in risk measure. What law invariance tells us is that if I have two portfolios and they have the same distribution, I'm going to assign the same risk value to these two portfolios. And then the question is, under model uncertainty, my framework, what would be the best way to define law invariance? And then I'm going to introduce the type of law invariance that will come up in this particular framework. So now this is basically the definition for risk measure. So risk measure, I'm going to use this rule to denote risk measure. I just define it on this set of random losses. You map a risk via model. In this case, P here, the probability measure here is kind of fixed or known. And then we map the risk to a number. And I said that risk measure is used for regulatory capital calculation, insurance pricing, decision-making optimization, and portfolio selection. And then when we think about risk measure, you first to think about the specification of X. Specification of X basically means, so what does X stand for in this case? Is it your portfolio risk? Is it credit risk, insurance, interest risk? But in this case, we assume that X head is just a portfolio risk, which is just the potential loss or gain that you have in a portfolio. And then the modeling of X basically talks about the distribution of the loss random variable. So now I said here there is a visible gap, which is in practice, neither X nor P is generally fixed. So a change in X basically means adjusting the position in your portfolio. And then a change in P means basically updating maybe the method that you use for calibration or for estimation. So in finance, both X and P evolve on a daily basis for a trading desk. But then in the literature, we then assume that, okay, P is kind of fixed, but in practice, P is not fixed. And that is what we want to consider here. So now that is what we want to consider here. Another motivating example is what I have here. So let's assume that a regulator gives let's say a portfolio, same portfolio to two financial firms. So this regulator gives this portfolio to two firms and then give them risk measure, let's say expected shortfall of 97.5, and tell them to compute expected shortfall of 97.5 of that particular portfolio. Because this portfolio, even though it's the same, is given to two different firms, because they have different modeling techniques, they are likely going to report different value for the expected shortfall of 97.5%, even though they are given the same portfolio. So that is one of the motivating example, which basically tells that basically tells us that why one is trying to compute the risk measure in a portfolio, then one should actually consider different probability measure in the quote or different scenario, which in this case, we are going to use this Q to denote. So this is what we know in the literature, and this is what we want to do. So this is my risk measure, which I call the generalized risk measure. So it's defined on X, which is my loss, and then given this set of probability measures. So, but in practice, P is always assumed to be fixed. So we just assume that we know P, which is not the case. Another motivating example is what happens with the Basel Committee on Banking Supervision. So for those that are familiar with the for those that are not familiar with the Basel Committee, so they are more like the regulator. And when we talk about the Basel Committee on Banking Supervision, we'll look at two players, the external players and the internal. So the external players are the regulator. So for example, think about in the banking sector, you can think about the central bank as the regulator for other banks in a particular country. So this internal here now is the financial institution. Now, the external, which is a regulator, what do? It's kind of similar to the example that I gave earlier. So they specify the rules for choosing the scenario, and then they specify the risk measure. So for example, they tell, okay, every bank should compute a special shortfall of 97.5 of their portfolio. So they specify the rules. Now, the financial institution, they have three main players: the risk analyst, the portfolio manager, and the model risk manager. So the risk analyst is the one that collects the information from the regulator, and then they model their scenario. Now, the portfolio manager will give the risk analyst the portfolio. So now this position of X, and then the risk analyst is going to evaluate the risk measure using the information from the regulator and using the portfolio from the portfolio manager. And then after evaluating for the risk measure, they will pass the results to the portfolio manager, who then optimize to choose the best position for internal needs. And this will then be given to the model risk manager, who will just backtest models. And then the final result that they have here will be reported back to the regulator, which is going to be their risk value here. Now, if we look at all the activities that happens there, the only thing that is fixed here is just the work of the regulator. Everything that happens with the financial institution changes on a daily basis again. And again, this basically tells that we can't fix a particular model P to evaluate your risk measure each time. This needs to change frequently. So this is another motivating example why we decide to study risk measure, whereby the risk measure is jointly defined on the set of random losses and then on the set of probability measure. So this is our new risk measure, which then we called generalized risk measure. So basically now for the generalized risk measure, you can see now that this is my risk measure, but now it's defined. I have two inputs here, unlike the classical risk measure, whereby you only have these two inputs, just one input. But in this case, I have these two inputs. And then these are just definitions. So the first definition here is standard. The generalized risk measure is standard if the risk measure on X given Q is equal to X. So here X is a constant. This basically tells us that if we want to measure, evaluate the risk on a constant, then it's going to be that constant. There's no ambiguity around that because your input is a constant. And then we have this what we call the single scenario risk measure. And single scenario risk measure basically tells that my second argument here, so you can see, this is a power set. So instead of having this power set in my second argument here, I'm only just going to consider this set P. So this P can just be like a subset of in this my power set. So a single scenario risk measure, again, is a generalized risk measure whereby the second input here is just a set of probability measure. And then we have what we call the core, which I will come back to later. So these are the properties of the generalized risk measure that I just introduced. So the first property is uncertainty aversion. Then we have the scenario monotonicity and the scenario upper bound. So the uncertainty aversion basically tells us that so the risk assessment increases as so the risk assessment kind of increase, the riskiness on a portfolio risk increases as model uncertainty increases. So we can see that this Q here is a subset of this R, which is then a subset of this P. And then if I'm assessing the risk on X given Q, so this should be less risky as if I'm considering assessing the risk on X given R, because Q is the subset of R. So it's kind of, the riskiness increases as model uncertainty increases. And then we have the scenario monotonicity, which says that under each scenario, so if I'm considering the risk on X under P, if this is less risky or smaller than the risk assessment on Y under the same P, then now this P is a single P in so let me, I think this thing is blocking me. Let me minimize, sorry, the video here. Okay. So again, if I'm considering, so this is as PA is Q. If this is less risky than this, then if I'm considering the overall risk evaluation on S given Q, it should be smaller than when I'm considering that of Y given Q. And the third condition, the scenario upper bound just says the overall risk assessment on S given Q shouldn't be as risky as if I'm considering the extreme case, which is the worst case scenario. But these are the three properties that pin down the generalized risk measure. And then, so what are examples of generalized risk measure? So this is a classical risk measure. This, for example, this is value at risk. So this is value at risk. This is the classical one. This is expected shortfall, the classical one. But now, under the generalized risk measure, this is going to be the representation for the value at risk. So now I'm considering the worst case scenario. And don't forget that in this case, my value at risk here is kind of defined on this, right? So I have these two inputs. So I'm considering value at risk of X given this set of probability measures. And it's the same thing for the expected shortfall here. So these are the worst case, in quote, value at risk and the worst case expected shortfall. And the natural question here would be, we already know, I mean, in the literature, we have worst case value at risk, worst case expected shortfall. How is this different from what we have in the literature? One answer is the following. So in the literature, worst case value at risk, these two premium here. So model uncertainty, they are kind of introduced into the framework as exogenous objects. They're not included in the modeling of, let's say, calculating the value at risk or expected shortfall. But in our own case, we are introducing model uncertainty as well as part of our modeling input, in the sense that this value at risk here is defined jointly on X and Q, and the same thing as the expected shortfall. So these are what we have in the literature. So some of these are kind of related to what we did, but not exactly the same. So for example, this book by Fomer and Sheed, here they introduce the robust traditional convex risk measure. This paper by Wang and Ziegel, they introduce the scenario risk measure. But in these papers, they introduce model uncertainty as exogenous objects. So again, there are lots of literature on decision theory under model uncertainty. Our work can be extended to this framework, but I'm not going to talk about that in this particular presentation because of time. And these are the work on robust portfolio optimization. For example, this paper by Ekaro et al. Basically talk about worst case value at risk. The one by Zhu and Fukushima talks about worst case expected shortfall. But again, their framework is more like a special case of ours, because in their framework, model uncertainty is introduced as a exogenous object, not like ours, where it's kind of like endogenous. So how can we characterize this generalized risk measure? So the result here is basically to show us how to characterize generalized risk measure. So what would be the structure of this risk measure that I just introduced? So for a generalized risk measure, which we use this both sides to introduce. So suppose our size is standard, then it satisfies uncertainty aversion and scenario monotonicity if and only if it admits this type of representation. And again, I think you've seen this already when I introduced the example for the value at risk and the expected shortfall. But this is just we establishing the result here. And it's the same thing if this size satisfies uncertainty aversion or scenario upper bound, then we have this kind of representation. And to prove this particular result, we just establish two different inequality here so that we say that this generalized risk measure is less or equals to this representation, then it's greater or equals to this representation, and then that gives us this particular result. So henceforth, if I mention the characterization of generalized risk measure, I'm basically just referring to this representation that we have here. So another important thing that I think I should talk about is the cause. So the cause corresponds one-on-one to the standard generalized risk measure that satisfies uncertainty aversion and scenario monotonicity. So the cause basically means when we define generalized risk measure, but in this case, we define it on these two arguments as our input, the set of random losses and then this set of probability measure. So generalized risk measure is when we define this psi on this set of random losses and then this power set. But when we reduce this to this P, then that is a single scenario, and then we call that a core if it satisfies uncertainty aversion and scenario monotonicity. And we just did it just to simplify the process, which means going forward, all the results, if this psi, this risk measure, if it satisfies uncertainty aversion and scenario monotonicity and is standard, every result that we can establish under this score can actually be induced by the generalized risk measure under this particular structure. So hence for the generalized risk measure that I'll be talking about will be the one that will be defined on this, but it's the same thing works or old when we consider the risk measure on these two arguments. Okay, so these are just examples. Expectation type, this is the core, right? When you define expectation, again, look at the input. We have set of random losses and this P, and this induces this generalized risk measure of this same type of this type. Same thing for value at risk. Then, but I will mention this penalty expectation type because this penalty expectation type basically induces the generalized risk measure, and this representation is kind of close to what we have in former and sheet for traditional convex risk measure. But remember, in the former and sheet book, this convex risk measure, the definition is only defined on this X. So they did not introduce these as part of their input because then they assumed that the set of P's are actually fixed. Okay, so now let's quickly go through the law invariance property. Like I said during my introduction, so law invariance basically tells if I have two portfolios, then they have the same distribution, then I should assign the same risk value to these two portfolios. So it's another, an important properties in risk measure. So now that we are now considering model uncertainty, so the question is, what would be the formulation for law invariance in this particular framework? And in this particular framework, we end up with different types of or forms of law invariance actually because we are considering set of probability measures, and that kind of induced this question on evaluation of risk. So if I want to compute the risk associated to a portfolio, should I only consider only the distribution, or should I look at the distribution and then the scenario model, or should I just look at the distribution and the loss variable? And that informs these three types of law invariance that we have. So we have the first one is a strong law invariance. And what this strong invariance tells us is that if I have X, so X, the distribution of X is P, and then the distribution of Y is Q. And if they are the same, so X given P has the same distribution as Y given, sorry, this P had the scenario model. So if X given P, if they have the same distribution as Y given Q, then I'm saying that the risk assessments on S given P should be the same as the risk assessment on Y given Q. So this is strong law invariance. So this is more like, this can be reduced to the classical one, right? Which is I have X and Y, they have the same distribution, then they should have the same risk value, irrespective of the scenario model. Then I have the loss law invariance that says that I have, if X and P have this, S given P rather, if it has the same distribution as Y given P, then the risk value assigned to X given P should be the same thing as the risk value assigned to Y given P. And then the scenario law invariance tells me that if I have, so S given P, again, the same distribution as S given Q, then the risk assessment on S given P should be the same thing as S given Q. So one way to put this into perspective is to think of P and Q as a scenario. So for example, let's think of P as pre-COVID, and then let's say Q is, let's take P as COVID period. So P is when we have COVID, let's say not too good economy, and then Q is, let's say, post-COVID, when the economy has recovered from COVID. So P is not too good, Q is good economy. So what this is saying is that if S given P, so my portfolio X in a not good, too good economy, if it has the same distribution as Y in a good economy, then I should assign the same risk value to it. And then if X given, so this portfolio, when the economy is not good, if the distribution is the same thing as Y when the economy is not good, then I should assign the same value to S given P and Y given P. And then the third one says, I have the same portfolio X. In good economy and in bad economy, they have the same distribution. Then I should assign the same value, risk value to this particular portfolio. So when we look at these three conditions, we realize that the most practical ones is actually the loss law invariance, because if I have two portfolio in the same economy and these two portfolios, they have the same distribution, then it's natural for me to assign the same risk value to this particular distribution. The one that is less practicable is this particular one, because if I have the same portfolio with the same distribution and I'm looking at them in two different economy, bad economy and good economy, intuitively, a risk analyst is going to assign more risk to that portfolio in a bad economy than it would have done in a good economy. So this doesn't come too natural to us in terms of application. And then here we just try to group the kind of distribution, the kind of risk measure that we have into those that are strong law invariant, and those that are, loss law invariant, and those that are scenario law invariant. So it turns out that expectation and value at risk, they have strong law invariant, and then expectation type, which is more like the convex law and convex risk measure, is under loss law invariance, and then this kind of risk measure falls under the scenario law invariance. So I will skip this particular part, but the result here is basically that we have this equivalence between strong law invariance and then the loss law invariance and the scenario law invariance. So we tag the loss law invariance and the scenario law invariance as weak law invariance, and then we have the strong law invariance, and then we just establish that the combination. So you can actually establish that strong law invariance implies loss law invariance plus scenario law invariance, and also you can prove that combination of loss law invariance and scenario law invariance can give you weak strong law invariance, provided you are working within the standard Borel space. Okay, so for that representation, so here we just try to characterize the generalized risk measure, but now using the law invariance. So instead of defining our risk measure on set of random losses and the set of probability measures, we just want to introduce it on distribution set. That is basically how law invariance works. So here we just want to look at our results and then try to formulate it under strong law invariance, loss law invariance, and then the scenario law invariance. So let me just quickly introduce this notation. So this M here is just a set of distribution, and then this big sigma here is the set of traditional law invariance. So here, I just want to characterize. So this B1, if you still remember, this is the strong law invariance. This is a loss law invariance, and this is a scenario law invariance. So here we just try to characterize generalized risk measure that are strong law invariance, generalized risk measure that are loss law invariance, and those that are scenario law invariance. And so these are the properties there. So we said that if psi, which is our generalized risk measure, satisfies A1, this is monotonicity, and then this is A3, which is the scenario upper bound, and then the strong law invariance, if and only if there exists this traditional law invariance such that we have this representation. And to establish this, it's kind of follow from this property. So if you remember again, my generalized risk measure, I said the representation is what we have here, equals to we have this soup, but instead of this, we have this psi of x given p, right? That is what we have here. And if A1 and A3 holds, we're going to have that representation. And then using the strong law invariance properties, if strong law invariance properties is indifference, right, on the losses itself and even on the scenario, because all what it tells us is that once this portfolio, once they have the same distribution, then I'm going to assign the same value. And that is why we have this psi here. So instead of we have psi x given p here, then we just replace it by this law invariance. And it's just the same idea to establish the proof for this, the loss law invariance, and the same thing for the scenario law invariance. So as an example, before I round off, as an example, I will introduce the coherence risk measure, but now I will introduce the generalized coherence risk measure, which basically means coherent risk measure, but now in our new framework. These are classical properties of coherence risk measure. So we have the monotonicity, cache additivity, positive homogeneity, and subadditivity. And then we have
try and round off. You have less than 5 minutes.
Okay, thank you. I think I should be able to finish this part before that. Okay, and then we have the combinotonic additivity. And then, so these are the 5 properties that we have. And then to pin down the one that is coherent risk measure. So if a risk measure satisfies the first 4 here, monotonicity, cache additivity, positive homogeneity, and subactivity, then that risk measure is coherent. And if it satisfies just 1 and 2, then we say it's monetary. Okay, and then we have this additional property, which we call activity of the core. This is what it tells that if I want to compute the generalized risk measure on 2 portfolio x plus y given p, is the same thing as saying I want to do it for individual. This is a very kind of strong property, but we need this property to be able to pin down the coherence property, the coherence risk measure. Okay, so this is the result here. So a standard generalized risk measure psi here satisfies, again, A1, monotonicity, the scenario, uncertainty aversion, the monotonicity, and then we have B1, which is strong law invariance, C1 here, which is the monotonicity that we have here, and then the C0, and then the C0, which is the additivity of the core, if and only if it's given as this representation. So coherent risk measure is represented as this. How do we establish this? If generalized risk measure satisfies A1 and A2, again, we have this representation, but now we have psi x given P here. And then it is known in the literature that if a risk measure satisfies law invariance, monotonicity, additivity, that risk measure is likely going to be of expectation type. And we use that property to pin down the expectation that we have here. And that is how we establish this coherent risk measure. And it's not surprising because this type of risk measure is, they've used it, it's being used even in practice. And I'm talking about the generalized risk measure. It's being used in practice, just that it has not been formulated or characterized in the literature. And that is basically what we did in this particular paper. So I will skip this part and and then to finalize or to finish off here, I will just talk about the connection to decision theory. So again, what we did is on risk measure, but this can be extended to literature on decision theory. And the idea would just be to compare a risk and a set of scenario and another risk with another set of scenario, which we actually formalize, and we have the result in our paper. But because of time, then I will just keep this part of this talk, and I will just finalize. So in summary, what we did is that we introduced a new framework for risk measure, whereby risk measure can be defined jointly on the set of random losses and the set of probability measures. And we call that risk measure generalized risk measure. And then we characterize this type of risk measure. We have a representation for it, and then we are able to come up with what law invariance looks like in our framework, which is we end up with 3 types of law invariance. the strong law invariance, the loss law invariance, and the scenario law invariance. And it turns out that the loss law invariance seems to be more practicable, in terms of application. And then we extend our results to decision theoretic outlook. And that is all I want to talk about. Thank you all for your attention.
Thank you, Tolu. Any questions for Tolu?
Yeah, I have a question.
Right,
Hello,
please.
how are you doing? I hope
I'm
you're
very
doing
well, thank you.
well. Very interesting study. You said you published the paper, is that?
Yeah, in finance and stochastic.
Okay, all right, so I can check it out.
Mm-hmm.
Wanted to just when you were talking about the invariance, law invariance, and you used as a practical explanation to help understand. You said if post-COVID and
Mm-hmm.
during COVID,
Mm-hmm.
I'm wondering, when you said they will have the same distribution, I'm wondering the issue of extremes, the tails, because definitely during the COVID, the tails are a major problem, and that is a dominant factor in the distribution spread. So you said as an example, kind of, I don't know, it doesn't really blend or it doesn't really fit in or suit in what I'm thinking, because the tails are going to be very dominant during the COVID and way less dominant during the bulk will be more dominant during the post-COVID. So when you said the same distribution and then use that may be something you may want to check out.
Yeah, so in this case, no, we are considering two different portfolios, but we are looking at portfolios that are kind of like related. So for example, like this X given P and this Y given P now. So X is a portfolio, Y is a portfolio. If they have distribution, that means they kind of behave like in quotes in a similar way. So even during COVID, the two portfolios, they're going to have heavy tails.
Okay, that's for loss invariance, but for strong law invariance,
it's the same thing. It's the same thing from strong law invariance, because what we are saying here is, okay, we are saying that S given P, right, and Y given Q. So I'm saying that P here, okay, now I think I understand what you're saying. So we have X given P, which is let's say this is during COVID, and we have Y given Q, which is good economy. And then we said that if these have the same distribution, strong law invariance is telling us that you assign the same risk value to the two. And what you said is actually the reason why we said strong law invariance and scenario law invariance, they are not, in terms of in application, they are not, you cannot apply them in a way. You understand what I'm trying to say? Because it's saying that irrespective of the economy, whether they are good economy or bad, like you said, whether they have fat tails or they have light tails or thin tails, we are going to assign the same risk value to it, which ideally it doesn't sound realistic. And that explains why I said, in terms of application, strong law invariance is not is not the optimal model to actually use. And same thing with scenario law invariance.
Okay.
But the loss law invariance, then this is why the loss law invariance comes more, highly recommended, because for loss law invariance, like you said, we are considering these two portfolios that kind of behave the same way. So in this particular bad economy, they are going to behave in the same, like, it's just like you looking at insurance company, people making claims during pandemic. It doesn't matter whether you have, so I can't remember, I'm trying to think of different insurance companies here that we have here in the US, but it doesn't, whether you are using the United Healthcare or you are using the Aetna, it doesn't matter whichever insurance company that you are using. Insurance company, they went through the same thing or the same ordeal during pandemic, right? And then that is why when we expect to assign the same risk value to whatever is going on, because even though they are two different companies or portfolio, their distribution is the same thing. So whatever A is going through, B should be going through the same thing. But when you now look at strong law invariance and scenario law invariance, what they are saying is not actually, as in you can't apply it. For example, scenario law invariance is saying, I have a portfolio during COVID, the same portfolio after COVID, and I want to assign the same risk value to these two portfolios. It's not realistic. A risk analyst is not going to do that. you're going to apply more risk to that portfolio during COVID that you would have assigned to it after COVID. So I agree with what you just said, and that explains why I said strong law and scenario law, they are not, in terms of application, they don't really come highly recommended, unlike the loss law invariance, which seems to be more practicable.
All right,
Okay,
guys, let's take a break now because we only have two speakers left, Daniel and Hebdi. So thank you, Tolu, for a very interesting talk. I mean, this is also my area, but we will talk about it later.
Okay, thank you so much for having me.
Yeah, pleasure. Can we take a half an hour break and come back in 30 minutes, okay? We just have two more talks, one by Daniel and the other one by Hebdi from Arizona State.
Yeah, it's okay, Prof.
All right, thank you. See you guys in a minute, few minutes.